Hello class, in this video I'm going to teach you about limiting reactants, right? And then I'm going to teach you how to identify them mathematically. It does get a little bit abstract, so bear with me, and thank you very much for watching this video. Let's start with a very simple question. What in the world is a limiting reagent? I stole this picture from Khan Academy, but it's a very simple picture, very similar to the little ice cream picture I did in class. So here I have 5 hot dogs, but I only have 4 buns. So with 5 hot dogs and only 4 buns, we can only make 4 hot dogs. Seems pretty easy because we run out of buns. That makes the buns the limiting reagent because it's the stuff that we're going to run out of. It's the thing that's going to determine how many total hot dogs are made. And the stuff that's left over, we call that the excess. Pretty easy to understand with hot dogs. It gets a little bit convoluted when we look at a chemical equation. For instance, let's go with a very simple chemical reaction where iron and sulfur come together to make iron sulfide. Given 9 grams of iron and 8 grams of sulfur, what is the limiting reagent and what is the excess? Now, a noob will totally think that it's the sulfur because there's so very little sulfur, but because there's only 8 grams as opposed to 9. But that's not the best way to think about it because chemistry occurs in moles, right? We know that chemistry occurs in moles, right? So let's first convert 9 grams of iron into moles and then 8 grams of sulfur into moles, and let's see which number is actually smaller when we think about moles, right? Just to make things a little bit convenient for us, I already found all the molar masses. The molar mass of iron is 55.845 grams per mole, and the molar mass of sulfur is 32.0656 grams per mole. Right, so let's do the maths really fast. Let's start with one of the givens, which is 9 grams of iron, right? And let's just do the simple dimensional analysis, right? We're given grams of iron, so let's let's cancel out the grams of iron by putting grams of iron on the bottom. And we know we want to get to moles, so let's put moles of iron on top. And let's find the values that will make them equal to each other. 1 mole of iron is equal to 55.85 grams of iron. Okay, 845 for all the kids out there who can't stand that I skipped a number that I rounded, right? So, and then if we do this little bit of math, it's just 9 divided by 55.845. We get 0.161 moles of iron. One down. Let's try the other one. 8.00 grams of sulfur. Let's get out of grams by putting grams of sulfur on the bottom, moles of sulfur on top. I know that 1 mole of sulfur weighs 32.065 grams. So I just have to divide because it's on the bottom. 8 divided by 32.065, and I get 0.249 moles of sulfur. So 0.249 versus 0.161. Iron. This one is a smaller number. The limiting reagent is iron. That makes sulfur the excess. Seems simple enough. How many grams of iron sulfide is produced? Well, at this point, we work off the limiting reagent, right? We work off 1.61 moles of iron, and we know that's going to determine the product. So 0.161 moles of iron. And we want to convert that to iron sulfide. So let's get out of moles of iron. And we can go into moles of iron sulfide. And if you look up here, it's got a 1-to-1 ratio, right? You don't see the ones, but the ones are there, trust me. So a 1-to-1 ratio, so now I'm in moles of iron sulfide. Let's get out of moles. The problem wants grams. So let's get out of moles of iron sulfide and into grams of iron sulfide. And every 1 gram of iron sulfide weighs 87.0 0.91 grams. If you're wondering where I got that, I added the molar mass of iron and the molar mass of sulfur together. It's the procedure that I think most of us in class knows. You're just adding up the molar masses from the periodic table. So if I do this math, 0.161 times 1 divided by 1 times 87.91, and I get 14.15 grams of iron sulfide. There you go. All right, so I found out the limiting reagent by converting the reactants into moles. I took the smaller number, that is the limiting reactant, and then using that I go through the rest of my stoic to figure out how much product is made. Hope that's simple enough. But this equation I only use like a simple 1-to-1-to-1 equation. Let's try one more example where we have coefficients in the chemical equation. In sample 2, 10 grams of aluminum and 10 grams of chlorine are combined, and it makes something called aluminum chloride, right? Aluminum and chlorine makes aluminum chloride. Identify the limiting reagent and the excess. So the same thing goes. Let's first convert to moles. Let's just simplify things by putting all the molar masses on here. I know that aluminum weighs 26.98 grams per mole. I know that chlorine weighs 70.91 grams per mole. All you got to do is you look at chloride on its own is like 35 grams, right? So just multiply that by 2. And then aluminum chloride, I know this one has a molar mass of 133.34 grams per mole. Okay, so now we have basically all the kind of core numbers that we need to do our math. First step is to convert to moles. Convert these reactants, right, these grams of reactants to moles. So let's start with 10 grams of aluminum. Let's get out of grams of aluminum into moles of aluminum, right? 1 mole of aluminum is 26.98 grams. 10 divided by 26.98 is equal to 0.371 moles. Okay. And then let's do the same thing for chlorine. 10 grams of chlorine. Oh, I didn't do the problems very well. This is technically 1 sig fig. Don't sweat that. Right? 10 grams of chlorine. Let's get out of grams of chlorine. Go into moles of chlorine. And I know each mole of chlorine weighs 70.91 grams. So 10 divided by 70.91, I get 0.141 moles of chlorine. This is moles of aluminum. You know, we're not done yet. These 2 moles refer to the total moles that you have for these things, right? But if you look at the chemical equation, it's not a simple 1-to-1 ratio. So here we have 30.371 moles of aluminum, and here we have 0.141 moles of chlorine. But we also know that it takes 2 aluminums, 2 parts aluminums and 3 parts chlorine to make 2 things of aluminum chloride, right? 2 parts aluminum and 3 parts chlorine. So ask yourself, what is 1 part aluminum, right? What's 1 part aluminum? So we just have to take this number, 371, divided by 2. So 0.371 divided by 2. So 1 part aluminum is 0.185, okay, or 186, all right? And then what's 1 part chlorine? If 3 parts chlorine weighs 0.141, so 0.141 divided by 3, so this is 0.047. This number is way smaller than this number, so we know that chlorine is the limiting reagent, right? This thing is the limiting reagent, all right? Because if I just think about 1 part chlorine is super small, 0.047. Okay, now that I've identified the limiting reagent, which is chlorine, and the excess being aluminum, how many grams of aluminum chloride is produced? Well, let's start with something that we know. We know that we have 0.141 moles of chlorine gas. 0.141 moles of chlorine. Let's get out of this chemical. Let's get out of chlorine and into the chemical we want, which is aluminum chloride. So let's get out of moles of chlorine into moles of aluminum chloride, AlCl3. All right. And looking at the balanced equation, for every 2 aluminum chloride, there are 3 chlorines. So, all right. So there are 3 chlorines out here for every 2 up there. And then that's going to get us into moles of aluminum chloride. Let's convert out of the moles of aluminum chloride and into grams of aluminum chloride. And I know that each one weighs 133.34 grams, right? Every 1 mole of aluminum chloride weighs that much. So let's finally do this little bit of math. 0.141 times 2 divided by 3 times 133.34, and I get 12.5 grams of aluminum chloride. That is how much that is made based on 0.141 moles of chloride. So, in conclusion, when we work with limiting reactants, first start with a balanced chemical equation. That's true. And then you got to find it in moles, right? The grams don't really matter, right? You want to see which reactant has the smallest number of moles, right? And sometimes when when it's not a 1-to-1 ratio, divide by the coefficient in front of each reactant, and that smallest value is the limiting reactant. And then we use that value to do the rest of our stoich. I know this is a little confusing. Feel free to rewatch it over and over again. And thank you very much for watching.